Now, moving along, it's time to take a look at some dynamical systems using the vocabulary that we've acquired so far. And we're going to start with what is the most simple example usually used in a pedagogical context, in which we have an intuitive understanding of the system that we are looking at. The system in question is the simple pendulum, and you can see the simple pendulum going here. We're going to consider this system, which I presume is intelligible to you, under a lot of simplifying assumptions. So, some of the simplifying assumptions we're going to make are that the rod is very light but rigid, that there's absolutely no friction at the hinge at the top, the weight at the lower end is heavy but very small and point mass, that it moves in a vacuum so we can get rid of air resistance, and that the force of gravity always pulls it straight down. Some of those idealizing assumptions are perhaps more realistic than others, but together they give us a system that we can characterize completely. How do we describe the state? Well, we're going to use two numbers to describe the state of the pendulum. One is A, the angle of elevation. So the pendulum moves usually along an arc, but if we give it a big enough kick, it'll go around in a circle, but it will never, the position of the bob will never be off that circle. So to capture its position, we need a circular variable A. And you can see in the diagram there the introduction of the Greek character pi. When we're talking about angular variables, we're talking about position within a circle, and there are, as usual, several conventions in use. A position within a circular variable is called phase. That heavily overloaded word, one of its technical senses, means position within a circle. And if you remember your high school mathematics, one way to describe that is describing the full circle as 2 pi radians. A radian is the length of the radius, so there's 2 pi times the radius in the circumference of a circle. That's why the numbers there go from 0 through pi at the top, and it will be 2 pi at the bottom, which is where the cycle restarts. There are other conventions for noting phase, and when phase is used in this sense, the convention doesn't matter. What matters is that we know that we're talking about position within a circle. The second thing we need to note to describe the state of the pendulum at any given time is the speed and direction of its movement. This is the rate of rotation, and it's a velocity, not just a speed. A velocity has a direction, so the pendulum can be spinning clockwise or counterclockwise, and we'll do this using positive numbers and negative numbers. And in theory, there's no limit as to how fast our pendulum is rotating. So this state variable contributes a real number to the state space. These two numbers are sufficient for our purposes, and so the state space now is a cylinder, as we noted before. The circular aspect to the cylinder describes position, and so there's one circle, one cross-section through this tube for each associated rate. Rate is the long linear axis. So let's rotate the little guy. Here's the pendulum hanging straight down, doing nothing. That too is a state, and we can mark it on the state space. There it is. It's at the circle, which corresponds to no movement, 0 rate, and is at the lowest possible position. And this pendulum isn't going to do anything unless we do something to it. So let's do something to it. We'll pick the pendulum up and move it a little bit to the left. Now we're going to hold it right there, a little bit to the left, so it's still immovable. We're holding it. But as soon as we let it go, it's going to start moving. So our initial condition is shown in the left figure. It's the dot on the circle corresponding to 0 rate. But it's displaced because we move the pendulum up to a different position in its cycle. Now we let it go. And you know what a pendulum does, so it swings down, and by the time it reaches the bottom, it now has a specific velocity. Therefore, when it passes the bottom line, it does so with a defined rate. That rate reaches a maximum, and as the upswing carries on to the other side, the rate will decrease until it finally comes to a stop. There we get it in the third picture, and that's the left-hand picture here. The pendulum has reached its maximum on the other side, and that's where it crosses the line of rate equals 0. Now it's going to reverse direction. So the velocity, which was positive, will now become negative. And it comes back down and crosses that bottom line again, this time in a different point with a different rate. In this case, the negative of the rate, which had passed over the line before. So you can see how the movement of the pendulum traces out a specific trajectory in this cylindrical state space. Now, cylindrical state spaces are not that easy to diagram. So we can make life easier for ourselves. There we go. Like someone doing crafts in primary school, we can take the cylinder and we can use our scissors to open it up, slit the toilet roll, open it up and spread it out. And this is what we see. There are some representative trajectories in this highly idealized, rather unrealistic pendulum. There you can see that there's a bunch of trajectories which are all continuous closed curves. I won't say circles, they're not circles obviously, but they are continuous closed curves. Two trajectories don't cross, and a pendulum which finds itself on one of these curves in the absence of any external intervention will remain on one of these curves forever. Now, 2 points are worth noting here in the state space. We can identify two very significant points. One is the very center. That's the point at which the pendulum is not moving. It's a point rather than a closed curve, obviously. But there's a corresponding point which corresponds to the position of the pendulum if it were raised vertically, so the bob is directly above the fulcrum, and immobile there. That point is obviously unstable. The slightest movement off that will cause the pendulum to carry on oscillating indefinitely. That point is shown on the slide twice. Remember, we cut the cylinder and we cut it right through that point. So when we spread the cylinder out, that point reappears on the left-hand side and on the right-hand side. And they're the dots which are shaded half black and half white. These are unstable equilibria, and we'll come back to them a little bit later. But our pendulum is very unrealistic because we removed all friction, all air resistance. We kept the entire universe constant while it was oscillating. We deny any external perturbation of this system, and so we have a thoroughly idealized system in which motion goes on forever. This is not obviously a real system. What happens if we relax our idealizations just a little bit? Supposing we add just a little bit of friction. Well, here's the state space before friction, and here's the state space after friction. I want you to compare these two. They are obviously similar, but they are interestingly different. Here, a pendulum swinging on one orbit will remain on that orbit indefinitely. Here, all orbits will tend towards rest at zero. So we've introduced something very, very new here. The ultimate fate of every trajectory here is to land at the center. There's one point, one starting point, that does not have that fate, and that is the unstable equilibrium point, when you have a pendulum which is impossibly posed, balanced on its head, as it were. It's worth examining the trajectories in this state space carefully. Some of them, the wavy lines, correspond to initial courses of the pendulum which go around in circles. If you give the pendulum a sufficiently large initial kick, it will circle and circle and circle and circle, and then at some stage it will oscillate and come down and settle to rest. So the qualitative nature of all trajectories is changed by this very small change in our idealization. No friction, friction. This kind of explicit representation of a deterministic dynamical system gives us a lot of confidence in our mechanical accounts, and I can't really pass up the opportunity to play you a little gif of Neil deGrasse Tyson. Okay, I apologize for that. We set up our system, we idealized the pendulum, and we assumed specific weights, lengths, gravity, and so on. Now we could alter those, and we could observe the change in the trajectories in state space. Usually, as we alter those smoothly, we will see smooth, continuous changes in the trajectories in state space. So if we increase the weight of the pendulum, or we decrease the length of the attachment, then those trajectories would deform, but the qualitative characteristics of all trajectories would remain the same. As you continuously change parameters, however, you may pass specific points at which a qualitative change suddenly occurs in the entire system. So if we were to reduce gravity, the speed of oscillation, the rate of oscillation would gradually reduce until that point at which gravity crosses the zero boundary, at which point everything would change, and the attractive equilibrium point to which everything tends would now be straight up in the air. As you change parameters, there's only a few distinguished kinds of qualitative changes that alter all trajectories that can occur. One is, we just saw one in which we went from a system with where every trajectory lived in its own world, as it were. We added a little friction, and suddenly all trajectories now had a common ultimate destination. So the system suddenly developed a fixed point. A system with a fixed point may develop oscillations, and that represents a qualitative change. And those oscillations may become irregular, or in a very specific sense, which we will dig into a little bit, they may become chaotic. But the transitions that can occur in a dynamical system as you change a parameter don't always lead to increasingly complex behaviors, as if we go from a fixed point to an oscillation to chaos. They may go the other direction. So we may have a system which is displaying highly complex behavior, which simplifies. And that becomes very important too. We'll be exploring all of these.